that space could not be empty. What we call the vacuum, what we call so-called empty space, could not be empty.
Does current quantum field theory account for this density? Haramein turned again to the Book of Gravitation, where he was surprised to find supporting evidence. Quote, present-day quantum field theory gets rid by a renormalization process of an energy density in the vacuum that would formally be infinite if not removed by this renormalization.
So, in current quantum field theory, it is necessary for the vacuum to have a very, very high density level in order for us to be able to run our equation and account for everything that's going on at the atomic level. That was a confirmation point for what I was already thinking about, that the vacuum is not empty, that space is actually a fluctuation that may be actually the source of our reality. But what is renormalization? Well, there's two kinds of infinities in physics. There's an infinitely small number. In general, a theory that comes up with an infinitely small number, the number can be discarded. It's not very important because it's a very, very small number. However, there's another thing that creeps up in physics, and when it does, it's called nasty infinities. And that is an infinitely large number. When an equation gives you an infinitely large number, you can't just say, I'm going to ignore that. So what is done usually, other than being said that the theory may be breaking down at that level, is that that number is renormalized. So usually what's used is a fundamental constant to cut the number. In this case, what was used was the Planck's distance. The Planck's distance is supposedly the smallest thing the universe does. You could think of it in really simple terms as the time or the distance it takes a photon to go across itself. It's the smallest wavelength the universe is supposed to be able to do. Do I think that the Planck's distance is the smallest thing the universe does? No. I think that the Planck's distance is a boundary condition that is a fundamental boundary in relationship to our experience. But I think that there's further definition, there's further structure below the Planck's distance. In any case, using the Planck's distance, which is 1.616 multiplied by 10 to the minus 33, extremely small, billions of times smaller than an atom, they renormalized the vacuum. What they did is they took a centimeter cube of space and they said, how many of these Planck's distances can we fit in, can we squeeze in into a centimeter cube of space? And if we do that, we'll have a finite number for the density of the vacuum. Basically, how much fluctuation of Planck's distances is there in a centimeter cube of space? So they stacked little Planck's distances full into a centimeter cube of space. Each one have a very specific mass, 10 to the minus 5 grams, and they added all up to get a fundamental density. The result was still extremely large. The result is 10 to the 93 grams per centimeter cube. That is an enormous number. You might have noticed in your bank account, every time you add a zero, it makes a big change. Imagine that you have 50-some zeros and you keep adding. At 93 zeros, right, you've got the density of the vacuum. Well, to give you an idea of how dense is that, imagine that you took all of the stars we see in the universe. There's billions of galaxies, they have billions of stars in them. Some of the stars are even much larger than our sun. And we took them all and we squished them all into a centimeter cube of space with like this huge trash compactor or something. You still wouldn't have the energy density of the vacuum, because the universe is approximately 10 to the 55th gram. So 10 to the 55th gram squeezed into a centimeter cube of space is still some 39 orders of magnitude smaller than the structure of the vacuum, the density of the vacuum. So to think of empty space as empty is incorrect. Space is full. It's full of these fluctuations. It's full of this energy density that is actually, according to what I found, the source of all of reality. The negative space is what produces our material world. Based on this, I started to think about it in terms of division of this vacuum density. I started to think of our reality not as object in the space, but as division of the space. I started to think maybe we could start to find patterns in the division of the space. Elizabeth Rauscher and I published a paper, and this paper described a scaling law. The scaling law is simple. On one side, we have energy density, and on the other, we have a radius. So the graph represents energy in terms of hertz in one direction and the radius in the other. And we started to plot all of the objects we see in the universe. We started with the universe itself. We ran the equations and we took the data that's available to approximate the radius of our universe. And then we approximated its energy levels, and we plotted the first data point. When you look at our universe, its size, and the amount of material in it, you find that actually our universe obeys the condition of a black hole. Our universe is too dense for light to actually escape it. If we were to shine a laser in our universe right now, it would get bent a little bit by our local star, our sun. Then it would eventually get to another star and get bent a little bit more. And it would get to another star and get bent by that gravitational field and get bent by gravitational fields of galaxy and all this. And because there's so much mass, there's so much matter in our universe, in its radius, in a closed universe, actually light would not be able to escape it. It would come back onto itself. So in fact, our universe can be considered as a black hole. Technically, it obeys that condition.
The universe, with its black hole condition, was the first data point Haramein charted. He next added galactic centers and stars. They lined up in a linear progression with the universe, an amazing result. If the vacuum is the source of the division, then it divides in very specific relationships. The next step was to see if the pattern continued on the other end of the physics scale.
Now we went from stars all the way down to atoms, right across the quantum world, from relativistic equation to the quantum world, and we plotted the energy level of an atom and its radius. And sure enough, the data point lined up again. Now that's a huge jump. And then we went all the way down to the Planck's distance, singularity, and that lined up as well. All the way from universe, which is immense, to a teeny point, billions and billions and billions of times smaller than an atom, and all this, all the data points in between, lining up so very closely to a perfect linear progression. Remarkable. Showing that there is structure, that there is order, that the vacuum is dividing in very specific relationships. And when we start to look at the relationship between the divisions of the data points, we found that the relationships were very close to phi ratios. The phi ratio is found everywhere in nature. When you look at your hand, the end of your finger is 1.618, which is the phi ratio, smaller than the second part of your finger. And the second part is 1.618, smaller than the third part. And your hand relative to your forearm, your arms relative to your body, and so on. Those Fibonacci sequence or phi ratios are found everywhere in nature, in plants, in flowers, the branches of a tree, the roots of a tree, the nervous system of your body, all of the divisions that produces all of the arteries and the veins of your body, and so on. All phi ratios, all Fibonacci series.
The phi ratio is evident even beyond where our eyes can see. The most recent discovery confirmed that the phi ratio exists even at the atomic level. Researchers in Germany observed that a chain of atoms acts like a nanoscale musical instrument, whereby the phi ratio seems to be the preferred division of the musical notes.
You are the event horizon.